Okay, effect of concentration on the rate. If you increase concentration, it increases the rate because it increases the number of particles per unit volume. Don't just say there's more particles, there's more per centimetre cubed, dm cubed. And that leads to more frequent collisions. It's all about collisions per second. Explain why most chemical reactions become slower as time goes on. The concentration of the reactants decrease as time goes on, so there's fewer frequent collisions. Or less frequent, I should say, less frequent collisions. Gas phase reactions may increase at a rate if the pressure is increased. So it's a similar thing, really. Pressure is really concentration in gases. If you increase pressure, you increase particles per unit volume, use that language again, so you have more frequent collisions. Here's our Boltzmann distribution. Number of particles on the Y, or molecules curve, kinetic energy on the X. I added a lower temperature one there, but I only wanted the higher temperature, so at 25. Higher temperature one, notice the peak is not as high, it's lower, but it's more pushed to the right. These never touch the x-axis this side, but they all should start at 0, 0, 0. So, activation energy, minimum energy required to start a reaction. Explain how the rate of a chemical reaction is affected by changes in temperature. At higher temperatures, more particles have energy higher than the activation energy. You see the activation energy here. If you have a higher temperature, you have more particles past that. So in that case, then you have more frequent successful collisions. It's all about frequency when it comes to rate. It's collisions per second. Quick labeled diagram there. If it's because it's negative, delta H points down. Activation energy there. Products, reactants. Define the term catalyst, a substance that speeds up the rate of reaction but it's not without being used up. 3 advantages, so there's less waste products. Catalysts actually mean you get a better atom economy. You make more specific products, a more obvious one, less energy is needed, so it saves energy, which could reduce cost. Okay, if that was the activation energy, that would be the activation energy with a catalyst. So that means we've gained all these particles here as well, which can now also react. So what is meant by the term activation energy? The minimum energy required for a reaction. More particles of energy exceeding the activation energy of a catalyst, so more frequent successful collisions. Again, going back to frequency. Okay, and then down here at the bottom, these arrows for activation energy with catalysts not always point up, there's always energy needed. So this one here is the catalyze reaction. Its activation energy has been lowered, that's the alternative pathway it's provided. So a catalyst provides an alternative route with lower activation energy. Over the page. Define a term rate of reaction. It's a change in concentration of reactants and products per second, or per unit of time, to be more general. And so I've plotted that graph like so. Okay, and then it says use the graph to calculate the initial rate of reaction, stating its units. So the initial rate of reaction is the rate when t equals 0. So this is something you have to do quite a lot in the second year, is gradients, so get used to it, especially initial ones. So here's t equals 0. We want to get the curvature of the line at this point. It's quite tricky to do. So clearly it's not like that, is it? It isn't, the line doesn't curve that way. It's not straight down like that. You have to get, so just the first couple of squares, you're following the routes. So I don't want to go right over it. I'm going to come away a little bit from the graph so I can get a pencil line down there. About, try and mimic it. And again, there will be a range allowed for this. I think it's about there. Okay, I might have been a bit sharp there. Maybe I'll move that slightly, a little bit more nearer to the line. I can go about there. Probably the second line is more accurate. Okay, so I've mimicked the curvature there, followed the curvature of the line, and I've gone down there. That gives me my dy. Go from 0 to 0.01. Sorry, 0.01. So dy. On my pen, let's go this. Dy equals 0.01. And then I'm going from 0 to, what was that then? 11, 12, yeah. So about there. So my graph, that's 11. Dx equals 11. So if I do that gradient then, it's always dy divided by dx. So 0.01 over 11, which is going to give you, my calculator out, 0.01 divided by 11. Okay, we'll make that 0.0009. And think about the units. This was in so up here. It was moles per dm cubed divided by minutes. Okay. So in this case, it's moles per dm cubed per minute. Okay. This wasn't. This was in minutes here. This was in moles per dm cubed. Okay, so we're now going to use a graph to find the rate of reaction after 15 minutes. So 15 minutes, you can go up here. So there's that point there. There's already a point there, so it's quite easy to find. And then find the curvature of the line again. So it's about like that. Giving myself a room to get my pencil line in. So this time, dy is 0.06, dx is 26.5. So 0.06 divided by 26.5. There's always some leeway on these. They allow ranges as long as they're sensible. So we got 0.06 divided by 26.5. So we got 0.0023, let's say, moles per dm cubed per minute. There we are. The last bit then, why is the rate after 900 seconds lower than the initial rate? Well, after 900 seconds, obviously, initial rate is always the fastest rate. The initial rate has the highest concentration of reactants. As the reaction goes on, the concentration decreases.